Hi everybody, this is Mr. Zarzak, and in this screencast I'm going to talk about electric potential, which is commonly known as voltage. So let's get right to it. We're now working in chapter 17 in the book. For this particular section, we do sections 17, 1 through 17, 8. So it's not the entire chapter. This is actually part of a bigger chapter outline. Regardless, read these sections and budget time to read them more than once. So go read these sections as soon as you possibly can, and then once we've gotten a little deeper into the curriculum, go back and read it again along with reading it before we get to our assessment. Okay? All right, so let's get started. Here we go.
You used to Google answers. You used to. Yeah. You used to Google answers on your cell phone. Late night when you needed help with physics. Google answers on your cell phone. Late night when you needed help with physics. And you know when the bullseye sings, I can't sing. That can only mean one thing. Target value. You know when the bullseye sings, I can't sing. That can only mean one thing. Target value.
There is a full-length version of that. If you're lucky or unlucky, depending on your perspective, maybe you'll get to hear the whole thing. Okay, so in our last unit, we defined the electric field as the force experienced by some small positive test charge. And so the big idea here is that a field is just a space where forces can happen. Okay, so if I bring in a little positive charge here and I put it in this field, okay, well, if I was going to let it go, it would get pushed this way. Remember, positive charges get pushed along the field. Negative charges would move against the field, right? Anyways, so the point is that in order to take the positive charge and to move it this way, okay, against the direction of the field, it's not going to do that by itself. A force would be required. A force to take this positive charge and move it some distance or to displace it. If you remember from our previous unit, well, that right there, that's the definition of work. Work is equal to force times displacement. And so all this says is that to take this positive charge and move it against the field, well, then you'd have to do work on it. Well, work is the change in energy. In which case, moving it against the field gives it what we call electric potential energy. Just like if we were to take something with some mass and lift it where there's a gravity field, so anywhere on Earth, okay, well, in order to do that, we'd have to do work on it, and we would change its gravitational potential energy. So that's the idea. So in the presence of an electric field, we just consider the charge. In a gravitational field, we consider the mass. Remember, these are two just different properties of matter, okay? And so if I put in my little positive charge here, okay, well then we'd say that it would have more electrical potential energy here than it would here, all right? The analogy would be like lifting it against gravity. Now, of course, I'm taking a little positive charge and I'm moving it downwards in this particular case. Okay, well, what if we consider the other type of charge? So if we replace the positive charge with a negative charge, okay, well, the negative charge would naturally be attracted towards this positive charge. Remember, all we're really doing here is just reinterpreting the idea that opposite charges attract and like charges repel. So with the negative charge, again, if I just put it here, it would be attracted towards the positive. And so if I wanted to take and lift the negative charge in the field, I would be moving it this way. I would have to do work on it, and that work would give it potential energy. With the positive charge, it's just the opposite. See, so like charges repel one another, so if I let the positive charge go, it would get pushed this way by the field, and so really lifting the positive charge in this particular case is doing this, just moving the charge against the field, which requires force. And so with electrical potential energy, there's really two big tricky things. One, we have two varieties of charge. We have positive and negative. And so their behavior, where they have more electrical potential energy, is different. And then the other thing that's really tricky about this is the same thing that was tricky about gravitational potential energy, which is where's the 0 point? All right, well, for electrical potential energy, there's no specific defined 0 point in the sense that, well, these field lines here, Okay, well, where do these field lines end? Well, the answer is that they'll either keep going until they find a negative charge to terminate on, or they extend out to infinity. So where is that zero location? We don't necessarily know that. The good news is that even if we don't know that, we can still deal with changes in potential energy. We did the same thing with gravitational potential energy. We don't necessarily need to know where the ground is to look at the change in height of something. Okay, so let me show you what I mean here. Okay, so I'm going to use some old tricks to derive some new things. All right, so first thing is that when we talk about change in potential energy, okay, that's really about change in position within a field. Now we're talking about an electric field, but potential energy is still just stored energy. So here we're storing it in an electric field as opposed to a gravitational field. Okay, so remember that. Next, work is equal to the product of force times displacement. Okay, this still holds true. In fact, all of our old physics equations still hold true. And we're going to use them to build something new. All right, so if I look at the change in the work done on some charge, okay, I'm going to set that equal to force times delta S. Now, this delta S is displacement. Okay, and you say, well, wait a minute, what about D? D is displacement. Well, you'll see that what we're really doing is how the electric field can vary. Here we're looking at the uniform case. Okay, well then not the electric field isn't always uniform. All right, and so this displacement thing can get a little tricky depending on what the field looks like. And really what we're doing here is we're looking at this in the way that we would derive this using calculus. In calculus, the D is a letter that's reserved for when you're integrating or taking derivatives, which if you haven't seen that yet, don't worry about that. Okay, just remember that this delta S is really just some small displacement. All right, next thing. All right, the electric field is defined as the force per charge, and so the force that acts on a charge in an electric field can just be found by taking the product of that charge times the magnitude of the electric field. The thing is here is what this is right here is this is really just the definition of an electric field. And so like if I took and I put a little positive charge in my electric field here, okay, well, we know that it would get pushed upwards. All right, well, when we do work on something to give it potential energy, we have to do work against the field. So in order for this positive charge to gain potential energy, we would need to take it and move it in this direction. Okay, it's not going to move by itself, so that means we would have to apply a force to it. Like we would literally have to push it down because the field is pushing up. What that means for us is that the force that we need to apply to do our work is in the exact opposite direction of the electric field, okay? And so we throw this little negative sign in here to indicate that. The force that we need to apply on the charge is going to be in a direction that is in the exact opposite of the electric field. That's all this means. Now, I know this is already looking a little bit confusing here, but I promise in the end this is all going to be worth it. Okay, the deal is that what we're really doing is we're relating electric field to energy. And the good news about energy is a scalar. So that's kind of where we're going. See, when we have a little positive charge, if we move it through a field, okay, well then if I say take my positive charge and I move it down like this, well, it's going to gain electrical potential energy. Well, just like with gravitational potential energy, how we get from up here to down here doesn't make any difference. Our change in potential energy is going to be the same whether or not we move in a straight line like this or we follow some crazy path, almost like we were moving along the track of a roller coaster or something. Okay, so anyway, so that's the idea is that it's path conservative. How you get there doesn't matter. It just matters on direction relative to the field. Okay. All right, now it's time for a little bit of substitution, and when we do this, this is going to end up making our lives a little bit easier, at least in terms of an equation. All right, so quick recap. Work is just equal to the product of force times displacement. Remember, this is just force times displacement, and the force that we need to apply is in the opposite direction of the electric field on some charge. Okay, so if I take, see, I have both of these equations have force. Okay, so if I sub in this little negative QE here, all right, there it is. So this negative QE times displacement is equal to the change in work. Okay, and work is change in energy, so we can talk about this work as the change in potential energy, and we wind up with this. Okay, this is the relation we're going to focus on right here. The change in the electrical potential energy is based upon negative QE times the displacement. All right, and so what we do is we take this little q and we divide it into the change in potential energy. And this right here, okay, this is what we're really interested in here. It's the change in potential energy per charge. Any charge that we put in the field will undergo some change in potential energy if we move it against the field. That's what this says. All right, so I've got a couple of red arrows here. It says potential energy per unit charge. Okay, gives us this. Well, this we're not so interested in right now. It's this relation right here because, well, this right here, this change in potential energy per charge, this is what we call electric potential, which is commonly known as voltage. Now, most people, the first time they see this, they get a little bit confused by this. So if you're in that camp, don't feel bad. It takes some time for this stuff to make sense. Okay, this thing that we call electric potential is just the electrical potential energy per unit charge. Now, this electric potential is different from electrical potential energy. So if the things are different, why do they make the names so similar? Well, the idea is that all of this stuff is derived using the same approach as we would do with gravitational field. Okay, and so if you remember, gravitational potential energy is equal to mgh. Well, we could talk about the gravitational potential as the gravitational potential energy per mass. And so it's like taking mgh and dividing out the m, in which case the m just factors out and we're left with this gravitational potential is equal to g times h, or the gravity field independent of mass. Fantastic, awesome. Why do I care about that? Well, here's why. All right, when we're dealing with electric fields, when we're dealing with charges, okay, we're talking about things that are very, very small in terms of both mass and very small in terms of charge themselves. So how do you keep track of individual electrons? The answer is that you don't. Okay, the way that you control electrons is not directly, but what you do instead is you control the space in which they occupy. And that's the thing that we can have control over. So it's an indirect approach to get things that are too small for us to see, too tiny for us to count. It gives us a way to control their behavior by controlling the space in which they exist. Okay, and that's really what's useful about this, along with the fact, of course, that it connects us back to energy, which is just maybe the biggest concept, the most powerful tool that we have in all of physics. Now, before we go any further with trying to deal with voltage, I actually want to take a step back here and talk just for a minute about gravitational potential energy. I'll bet you there were many of you that when we introduced gravitational potential energy as mgh, wondered why is it that we don't plug in a negative 9.8 for the g? Why is it that we drop it here? Okay, so I'm going to take a step back here and look at the good old free body diagram for something that has weight, which is just mg. Well, the deal is that if we want to give something that has weight gravitational potential energy, what we have to do is we have to lift it up. So we would just be applying some force to this, okay, to make it move upward as a constant velocity. And it just so happens that the force we would need to apply would be the exact same magnitude but the exact opposite direction of the weight. It's almost like the force that we would need to apply would just be the opposite of the weight. Okay, and so since this little negative sign, that's our direction. Okay, we need to apply a force in the opposite direction of the weight, and well, the weight's going to be down. So technically, when we do this, the negative 9.8 is in here too. It just so happens that there's a little negative sign here that we deal with, and so the negatives cancel. And because they factor out, we just never really bother. That's the reason. So bringing this back to electricity. Okay, so super fast recap. We took advantage of work is just equal to the product of force times displacement, where the force that we need to apply is in the opposite direction of the electric field on some charge. And so that gets us to this change in potential energy per charge is equal to this E times displacement just in the opposite direction. Okay, well, this change in potential energy per charge, that's the important part. And so whenever we come up with a useful expression in physics that gives us some quantity that we can use, we give it its own name, we give it its own variable. And so we have this delta PE per charge, that's the electric potential, which is commonly known as voltage. This V here is for voltage, okay? This is the mechanism that we use that will come back a little bit later on, but honestly, for the time being, we don't really care about this anymore. We will again in a little while, all right? But this is really the important part. All right, now we've got a definition for electric potential, we've got a definition for voltage. And so what we do is, because we've already got all these different equations, we've already got all these laws like conservation of energy and work as change in energy that can include potential energy, we just take and write this in a little bit different form. This is really old stuff. We've got this already. Okay, all we're doing now is we're connecting this to charge, electric fields, electricity with this concept of voltage. Work is equal to the change in potential energy, that's electrical potential energy, which we can find by looking at how a charge experiences a change in voltage. That's what this says right here. Charge experiencing some change in voltage. Slap those two together, we got the change in potential energy, which means we got the work. That's the connection. And so to stick with this idea of drawing comparisons between gravitational potential energy and electrical potential energy, okay, remember mass is just the quantity or the property of matter. Well, now we're talking about charge. And when we computed gravitational potential energy, it was mgh. So the gh, the product right there, that's like the change in voltage. That's the analog. So fantastic. So then what the heck is voltage? All right, well, one definition that I came up with a number of years ago is it's a way to quantify a predictable response. And before you get angry at me, let me tell you what I mean. All right, how many times when we would work an energy problem where we would say use potential energy becomes kinetic energy and then the mass would factor right out? In other words, we didn't need to know how much mass we would have to figure out, say, how fast something was moving later on. It's almost like saying if I took a 1 kilogram mass and a 1,000 kilogram mass and I dropped them both from the same height, well, when they hit the ground, they would be moving at the exact same speed when they got there. We could make that calculation, we could do that prediction without knowing the mass because it factors right out. Well, that's the idea here. With voltage, it allows us to make predictions about how a charge is going to behave without actually having to know the quantity of charge that we're talking about, whether it's one electron, a gazillion electrons, 45 microcoulombs, whatever. None of those numbers matter because we can factor them all out using voltage. That's why we care. That's why we say it's a way to quantify a predictable response. It's a way to put a number to what charges are going to do that we cannot see, that we cannot necessarily count. Got it? So just a quick note on units, since voltage is the new thing, we need units for voltage. I'm sure many of you are aware of this, but voltage has the units of, well, the volt. But that's an honorary unit, just like a Newton is an honorary unit or a joule. The volt is named after a scientist by the name of Alessandro Volta. That's a story for another time. But for voltage here, okay, remember we define the change in voltage as the change in potential energy per charge. Okay, so from that perspective, okay, well, we know what the units of potential energy are. That's the units of the joule. All right, and we know what the unit of charge is. Charge is measured in coulombs. Okay, so the units of voltage is the volt. And so 1 volt is equivalent to 1 joule per coulomb. We could certainly take it and expand it out from there, but honestly, the farther we take it, the more disgusting this gets. But we've come this far, so why not? You probably remember hearing a pretty terribly awesome physics joke about the joule, which is someone that Newton needs to meet. If you remember Newton meter, she's a joule. Or if you remember, work is force times displacement, so Newton is force and meter is displacement. So we could also write a volt as a Newton times a meter per coulomb, which doesn't really do much for us. But hey, we're just going crazy here, so we're just going to continue. You remember that Newton is the unit of force, which comes from Newton's second law as mass times acceleration. The units of mass, if you remember, is the kilogram, and the unit of acceleration is the meter per second squared. And if we took that and multiply that by the meter and divided that by the coulomb, okay, well, that right there is what a volt is. If I want to take this and try to make this a little bit cleaner, unfortunately, it really doesn't get much cleaner from here. I could take this and write this as a kilogram meter squared per second squared times a coulomb, and that would be equivalent to a joule per coulomb, which is a volt. That all of this is just disgusting, not quite so disgusting, but still disgusting. If you know that a volt is a joule per coulomb, be happy. That's far enough. Okay, so all this torture. Why? Well, at the end of the day, using voltage actually makes our calculations a lot easier. So let's look at a sample calculation so that at least we can take a little breath. All right, so a pith ball with a charge of negative 25.0 nanocoulombs is slowly moved 1 meter in an electric field. It goes from a potential of 0 to 100 volts. How much work is done on it? All right, so our new friend here is work as change in potential energy is equal to the change in voltage times the charge. Okay, so it's asking about work, so what we're going to do is we're just going to take and set the work equal to the change in voltage times the charge. All right, so work is equal to the change in voltage, where I'm going to write change in as final voltage minus initial voltage times charge. All right, and it's going to make it a little easier if I zoom in a bit here. All right, so work is equal to, let's see, so we're going to end at 100 volts, and we started at 0 volts, and we've got negative 25 nanocoulombs. So we're going to end at 100 volts, and we started at 0 volts, and our charge is negative 25 nanocoulombs, 25 nanocoulombs, so that's negative 25 e to the negative 9th. Nano is billionth, or 10 to the negative 9th power. Okay, and so calculation-wise, all I'm doing is taking 100 times negative 25 times 10 to the negative 9th. If I expanded that out, I would get negative 2.5 times 10 to the negative 6th, and this is work, which is measured in joules. If you remember, a volt is a joule per coulomb, and we're just taking a joule per coulomb times a coulomb, so the coulomb part factors out, and we're left with joules. We could also express this, since 10 to the negative 6, since we're talking metric prefixes here, we could also write this as negative 2.5 microjoules. Okay, so just different ways to represent the number. And remember, work is change in energy. Okay, and so this right here, this is our change in potential energy, because we've defined this voltage expression by change in potential energy. I've noticed too that when I solved here, I did keep the negative sign in for the charge, and that's important now. All right, we do need to keep track of that because, well, we have positive and negative work, and that's going to change depending upon whether the charge is positive or negative. Now, if we think about what's going on here, okay, the fact that the work is negative means it lost potential energy. So if I throw my little negative charge in here, see, because it says that the ball is slowly moved 1 meter in the electric field. Okay, so if I take my little negative charge here and I put it in the electric field, we got to think to ourselves, well, which way would it move in order to lose electrical potential energy? The way to do it is to think back to the beginning, where we started. Opposites attract, like charges repel. So if I take my little negative charge and I put it in this electric field and I just let it go, okay, well, which way would it move because of the field? Well, negative charges move against the electric field because opposites attract. This little negative is going to be attracted to the positive, and so just by itself, okay, it would fall downwards towards the positive, in which case it would lose potential energy. And in fact, that's exactly what we computed over here. All right, the charge loses 2.5 microjoules of potential energy. So that tells me something. The charge did this. Okay, it went down like this. Now, if you remember from energy, we know, okay, that energy always goes somewhere, so something needed to happen to this energy. So what the heck happened to it? So to answer that question, think about it like this. If I just took the little negative charge and I let it go, it would be attracted towards the positive. It would move towards the positives, but it wouldn't just move at a constant rate. It would speed up. It would accelerate. It would gain velocity. And so that loss in potential energy will become a gain in kinetic energy. So let me show you a little something with change in potential energy that will at first look a little bit unfamiliar until you understand what we're really doing here. The change in potential energy. So our charge lost potential energy, which means it gained kinetic energy. How much? Exactly how much it lost in potential. Okay, so this just says that the change in our potential energy is just equal and opposite to our change in kinetic energy. If I lose it here, I gain it over here. If I gain it over here, I lose it over here. What are we really looking at here? All right, well, delta is change, which is final minus initial. So if I just expand this out, final potential minus initial potential is equal to the opposite of the change in kinetic energy. So let's just expand that out too. Ke final minus Ke initial. All right, and let's go ahead and carry the negative sign through. So Pe final minus Pe initial is equal to negative Ke final. And then I've got negative times a negative, so that becomes a positive. So plus Ke initial. All right. And now, as a last little step, I think I'm going to group terms together. Okay, and so all I'm going to do is I'm just going to take and I'm just going to move this. I'm going to add this over to this side, and I'm going to add this over to this side. And lo and behold, we get something very familiar. The final potential energy plus the final kinetic energy is equal to the initial potential energy plus the initial kinetic energy. So what are we really looking at? Whether we're looking down here or whether we're looking up here, these are just two different ways, two different forms to write conservation of energy. Yes, conservation of energy is back. Okay, so I want you to think that when we studied electrostatics last unit, we were bringing back our analysis of forces. Well, now we're bringing back our study of energy and work energy theorem. So coming back to our little example here, notice that the given information says that it's moved 1 meter in an electric field, and we were able to solve this problem without using that 1 meter at all. Heck, we were able to solve this problem without knowing the value of the electric field either. Okay, because with voltage, it really doesn't matter. Our analog is that, well, voltage is this electric potential. So if we think about it in terms of like a gravitational potential as G times H, it's the mgh without the m. Okay, well, the voltage accounts for the G and the H. Okay, the 1 meter is the position. Instead of G, we're talking about the electric field. So honestly, it's really just the product of these two that gets us to the voltage. I don't need to know the 1 meter part at all to answer the question, and I don't need to know the electric field either. I just need to know the change in voltage. I can use this idea, though, to figure out where I have areas of higher voltage versus lower. So, like, this all goes back to opposites attract like charges repel. Okay, if I put some positive charge in this electric field, it's going to be repelled away from the positive charges that are the origin of the field. So if I just let it go, it would move this way. Okay, if I want to bring it to a higher electrical potential energy, I move it this way. A positive charge being moved to higher electrical potential energy means it's being moved to a higher electric potential or a higher voltage. Over here is at a higher voltage than over here. And if we think about it in terms of the previous example, okay, well, we took a negative charge, and if we let it go, it's going to move from 0 to 100 volts from a lower to a higher potential. Okay, the negative charge is going to do the exact opposite of what a positive charge does. Okay, so further evidence that when we talk about a voltage, this is going to be at the higher potential than this. What makes it tricky is that the positive and the negative charges behave opposite of one another. A positive charge will naturally move to a lower voltage. It's almost, the analog is like dropping something in a gravity field. It's going to move to a lower height. Okay, the negative charge just does just the opposite. Okay, it's going to move towards the higher voltage. All right, so for the negative charge, to give it more electrical potential energy, I would need to force it to move in a direction that is opposed to what it would do naturally. So over here, the negative charge has a higher potential energy, whereas the positive charge has the higher potential energy over here at the higher voltage. Okay, and last but not least, all right, all these example problems and everything we've derived has been derived in terms of a uniform electric field. And all that means is just that the electric field lines are straight, okay, and the field line density is the same no matter what. Okay, so the spacing between the lines here is the same as the spacing between the lines here, and here, and here, and here, and here. We call that uniform electric field. All right, we learned that the way that we get that is by charging up two plates, one positive, one negative. For voltage, all right, we defined voltage originally as in this: take a charge and move it in some displacement along a field in the opposite direction of the field, and we've got the change in voltage. Okay, that's what the little negative sign is. It's just opposite directions. So if we happen to have the case of a uniform electric field, okay, well then this actually becomes really, really useful in a really simple way. We say that the change in voltage is just equal to the magnitude of the electric field in the opposite direction. That's where we do the displacement. So if we know the change in voltage, we get this really simple expression where delta V is equal to negative E times D. All right, and this is a case for when the electric field is constant. Okay, and so much like work is equal to the change in potential energy is equal to the change in voltage. Okay, well now I have a relatively simple expression for the change in voltage in a constant electric field. All right, physics friends, this is Mr. Zarzak, and the screencast you just watched was Electric Potential Part 1, or Voltage Part 1. Thank you. See you next time.